In the last part of lecture unit 2.3, we define the moment of a couple and we look into some other properties of vectors. The theorem in point 2 allows us to define the moment M of a couple, also called a couple moment, as the vector M equal to R cross F, with R any position vector, with the tail on the line of minus F and the tip on the line of action of F. Since we have proved that the resultant moment M of the couple forces about any point reduces to a formula that is expressed in terms of a position vector between the lines of action of the couple forces. You will also remember that this position vector can be any vector as long as it extends from the line of action of minus F to the line of action of F. Up to this point, we have now encountered three types of vectors. And our first type are the position vectors. They are examples of fixed vectors, since the tip and the tail of the vectors are of the utmost importance. As an example, flying from Johannesburg, denoted by J, to Cape Town, denoted by C, can be described by a position vector JC. Flying from Cape Town along the same position vector JC will, however, end in a disaster. This shows that position vectors are fixed vectors. The starting point and the end point are important. Our second type of vectors are the force vectors. Now, force vectors acting on rigid bodies are examples of sliding vectors. As an example, pushing against a rectangular block on one vertical side has the same effect as pulling with the same force on the opposite vertical side, as long as the two forces share the same line of action. This means that the force on the one side can slide along its line of action to the force on the other side. This is true for rigid bodies, and the bodies do not have to be in equilibrium. And lastly, in this lecture unit, we have to find couple moments. So, couple moment vectors acting on rigid bodies, very important in equilibrium, are examples of free vectors. The moment of a couple acting on a body in equilibrium can be applied at any point on the body without changing the external effect on the body. This is, however, not true if the body is not in equilibrium. In point 3, we have to find the moment of a couple in terms of the cross product. There is also a scalar formulation for the couple moment. The magnitude of the moment M of a couple is given by M equal to F times D, where F is equal to the magnitude of the force F, which is the same as the magnitude of the force minus F, and D is specifically the perpendicular distance between the lines of action between F and minus F. The direction and the sense of the moment is determined by the right-hand rule. M acts perpendicular to the plane that contain the vectors F and minus F. This definition is in order, but we have to describe it in full, whereas the cross product definition is just one formulation, and from the cross product we are able to find all the scalars as in this definition. The cross product definition also immediately gives us the direction of the moment. In our next point, we will define equivalent couples. Couples are equivalent if they have the same moment. Since moments are vectors, it means that they have to have the same magnitudes and directions. Therefore, the defining forces that occur in pairs of equivalent couples all have to lie in the same plane, or if they do not lie in the same plane, at least the pairs must lie in parallel planes. In our last point, we will see how to find the resultant of couple moments. Now, couple moments apply to rigid bodies that are in equilibrium of free vectors, and therefore they may be moved to any convenient point. So if we decide to take all the couple moment vectors to the same point, these vectors are now all concurrent, and therefore we can find the resultant of the couple moments with vector addition. Note that the vector addition is not defined if the vectors are not applied on the same point.